The session, the first speaker is Stefan Groot Nibbelink, and his title is there, and I think we're for 15 minutes.
Good, so I would like to thank the organizer for this very nice conference. I will be talking about supersymmetry and Weyl invariance and how you can use that to get to the BPS equations directly from string theory. So I apologize for people that really were coming here for a phenomenological talk. This is really more hardcore string theory, I guess. So let me start with a motivation which is kind of rooted into what you are used to when you do all kind of compactifications and so on. What we then are always studying is what you get when you put the various variations of fermions when you put them to zero. So you have your variations in the heterotic theory of your gravitino, your dilatino and your gaugino. Put it into zero, these variations for non-trivial supersymmetry variations. That would then be some sort of interesting solution, and of course some of these cases we know very well. Where in particular the first equation implies that your geometry is complex, and then if you assume that you don't have any torsion, so h is equal to 0, then the dilaton is constant. You find the standard Clapeyron condition. In the case that there is torsion, so h is not equal to 0, then your dilaton via these equations also has to be non-vanishing. And then this is the so-called Schrödinger system, and one of the characteristic features that it has is that your geometry is then what is called conformally balanced. So there's in maybe this formula, a balancing between the determinant of your metric and e to the power your dilaton, that combined combination is constant. In addition, of course we know that when you have your gaugino variations, that putting it to zero, that implies the Hermitian-Mills equations, where in particular one important one is that you get f with holomorphic and anti-holomorphic indices contracted with the metric, that is equal to 0. Good. So the basic question that I want to ask and hopefully solve is the following. How do we really derive this from string theory? And the way it's normally done kind of indirectly, and there's only maybe at the first step string theory coming in. That's namely you start with your two-dimensional worldsheet, you use Weyl invariance or finiteness, and then you find your typically your bosonic field equations in 10 dimensions. And then what you do is you try to lift them to a low energy effective action. That is first of course an action only for the bosons. Then you try to supersymmetrize that, because you know in your spectrum that there's supersymmetry, but maybe not on the whole field theory. So you try to find your supersymmetry variations. Then of course you have to modify your action, and this goes back and forth sometimes. Then you finally find a consistent system done by these authors. And then of course you can put these SUSY variations to zero, and then you get this equation that I had on the first slide. So a natural question, and I was really wondering why this hasn't been asked a long time ago. Can you do this directly? Yeah. So directly from your worldsheet sigma model and to go to your to these BPS equations. Well, since what people most of the time use, and what I also will be using, is the RNS formulation. In the RNS formulation, you don't have any fermions, target space fermions explicitly. You find them in the spectrum, but they're not explicitly parameterized on the worldsheet. So you would think it will be a pretty hopeless thing to find these BPS equations, which are precisely putting these fermionic variations to zero. But then if you think a little further, you think, well, the equations which we really are getting from these, putting these SUSY variations to zero, these are equations for bosonic fields. In the RNS formulation of string theory, of course, precisely these fields are encoded, or at least a large set of those. And so when you think of in that way, you think of maybe there is a chance to get these equations. So let me first just state the main idea of how we want to go ahead, and it's kind of putting two old concepts kind of together. One is that finiteness and Weyl invariance imply the 10-dimensional equation of motions. I mentioned that already. And the other thing is that if you start with a worldsheet which has 2,0 supersymmetry, then automatically this the geometry, your target space geometry that you're describing, has a complex structure. Yeah, and that was one of the things that came from these BPS equations. So maybe what we can do is look at this renormalization of this sigma model, so the finiteness and this Weyl invariance, in a manifest supersymmetric 2,0 supersymmetric fashion. Yeah, and maybe this can give the BPS equations. So let's see if this can work. So to do that, I need to introduce a little bit of 2,0 supersymmetry. So at 2,0 supersymmetry, you have one complex Grassmann variable, say theta plus, and then its complex conjugate theta plus bar, then you have corresponding to that you have the supercovariant derivatives and the corresponding algebra. And then you can look at irreducible representations of this 2,0 superspace, and there are kind of two basic ones that we need. One are the chiral multiplets defined by this constraint, and the other ones are Fermi multiplets, which are in essence of course satisfy the same constraint, but here the lattice are fermionic objects, or the lowest components are fermions, and here the phi's, the lowest components, are the coordinate fields, which of course are bosonic. And then you can just say, okay, I have these things, I want to require this theory here is Lorentz invariant and scale invariant on the worldsheet, and then the classical action which you can write down is this, where k and n and some other functions which I didn't write down for simplicity are general functions of your chiral multiplets. Yeah. So that's just first what the 2,0 superspace action is. Then of course you want to ask, okay, what does it really describe? And that's kind of neat, because if you then go to components, you can just read it off, and you find that this action both describes a Hermitian metric on your target space via this formula, and of course it's explicitly Hermitian, as you can see. It describes a B field, and so you see that this k and k bar are prepotential for both the metric and the B field simultaneously, which I think is a neat fact of this 2,0 formalism. And in addition, these ends, they, in some combination, which is given here, describe our target space gauge fields. Yeah, so these bosonic fields are precisely encoded here. Good. So then, to do this thing, this question about finiteness, you take this theory here, you expand, you derive some Feynman rules, and if I want to do this manifestly supersymmetric, you get super graphs, super propagators, and whatnot. And then you can look at the renormalization of this thing, and then require when these things are kind of cancelled. Yeah. So let's do that first in a simple example, which are the kinetic terms for these Fermi multiplets, which have to do with the gauge degrees of freedoms. And then you have kind of these two graphs. So one graph you have here this vertex where you have your kinetic term 2 times differentiated with respect to the quantum fields, and then you have one quantum propagator for the chiral multiplet, and that is kind of in this formula encoded by this inverse metric. So you get this structure. And then there's another diagram like this on the worldsheet. In this case, you also have a propagator for the Fermi multiplet and one propagator for the chiral multiplet, so that gives you two inverses, and since it's a triple interaction, you have to end with one derivative, either holomorphic or anti-holomorphic, and that then gives you this diagram and this contribution. And as you kind of already can see, is that if you take these two combinations together, you precisely get the Hermitian field strength contracted with the metric, which is precisely what of course we know is part of the Hermitian-Mills equations. Then of course requiring that this theory is finite means that this beta function has to vanish in this case exactly, but it's an equation as a superfield equation, not just in a standard equation of motion. And so you find directly the equation of the Hermitian-Mills equations out, not the standard Maxwell equations. Yeah. And so what we really use here is that we do the renormalization of this 2,0 theory in manifest 2,0 off-shell way, and then you get more powerful equations, and a similar thing was also realized by these authors. Good, so you can do similar things for the kinetic term for your chiral multiplets. There the story is slightly more subtle. The diagram looks like this. So you have your background thing, it's kind of this tadpole for this derivative of phi. Again, you have your propagator, which gives you this inverse metric, and then this vertex in this case is a bit more complicated. It has kind of the derivative of your metric plus torsion. In this case, you cannot just say this has to vanish, because if a renormalization of this k here is purely holomorphic, then by doing this full superspace integral, it just drops out. So it only has to be holomorphic. Then you can combine it, and that's a little bit more detail, so you can find it in our paper. Weyl invariance that implies that this thing becomes proportional to the dilaton. Yeah, so you get a relation between this connection and this dilaton. And you can check that this is kind of encoded in part of the gravitino variation. Similarly, since we are doing expansion in quantum fields, classically, of course, when you do this expansion, you want to have that the tadpoles, so the tadpoles for the quantum fields are absent. Yeah, so that the theory starts with quadratic things in the quantum fields. But at the quantum level, these things are generated again, and those have to vanish again up to holomorphic things, which then get related again to the dilaton. So that gives us this equation. And this equation is precisely the equation that you get by of requiring that your di Latino, that one vanishes. Yeah, so this is directly the di Latino equation when you then combine it with the other equation which was on the previous slide. You get the consequences from your variation of your gravitino. And if you put these two together, you get precisely this condition which was related as the conformal balancing. Yeah? And so clearly, if then the dilaton will be constant, you get the original Clabeyao condition back. Huh? 3 minutes. Well, I'm essentially done. Good, so let me just summarize what we found. If you start with your worldsheet theory and the worldsheet you parameterize in a manifest 2,0 way, so that's of course a restriction, that's not a general worldsheet. And then you require finiteness or more specifically Weyl invariance of this theory. Then you directly find your heterotic BPS equations and you can kind of bypass all these things here. And the reason that I think this is useful is that so far I've discussed only kind of the equations that I get at one loop, yeah, and you saw that the calculation technically is pretty easy, they're very simple diagrams. So it's also really feasible to go really beyond one loop, or 2 loops, or maybe even higher. And then if you want to do the same thing kind of via this route, yeah, the conventional route, it quickly becomes very, very difficult, yeah, because you have here loop corrections, and then you have to see how you kind of incorporate it into your SUSY variation. You have to modify them, and nobody can do this really to a very high order. And our procedure really allows you to directly find these equations again. And secondly, since we are really using only properties from the worldsheet, even if you go to cases where your geometry or maybe your vector bundle or the combined thing becomes singular, where of course the normal kind of supergravity approaches where you assume that there's large volume, that there are no singularities, when this doesn't hold anymore, this approach or this kind of requirements that you get something which is still like n equals to 1 in 4 dimensions can still just work. Yeah, so in that sense it's also very powerful. Good, so with that I would like to close. Thank you.
Very much. Questions?
So you said, so your main requirement is 2-0 supersymmetry on the worldsheet. What does that exactly say about the target space? So you said something about complex.
Yeah, so what you do is you say, I want to have it, so you first investigate the representation structure of 2,0. Yeah, these are the multiplets which are allowed. There are others, but this is kind of the simplest one. Then you write the most general action that you can do, yeah, which are also compatible with Lorentz invariance and scale invariance. And then you just work without the components and you just find that it describes a Hermitian metric, so a Hermitian manifold with, in general, B field, so in general with torsion on it.
So the 10-dimensional space would be...
The 10-dimensional space, it depends on over what you let these indices run exactly. Yeah, so you could say part of it is maybe just let-dimensional, 4-dimensional Minkowski space, or as you like.
But I mean, so you don't mean the internal space. It's not.
No, these indices are really what I have in mind. Of course, there are the internal, describe the internal manifold. For the formalism, you see flat Minkowski space is also can be thought of as a 2,0 theory by itself. Yeah. And then it's also just included here. It's just a one specific choice for this k. Right? The k is just phi bar.
Because the BPS equations make a statement about the 10D, right? Not
yeah, so that's kind of here included. So they just yeah.
Maybe I ask you later before we get lost.
Sure.
I think I missed a very basic point. When you normally do this, so you go to this sigma model and compute the beta functions, you get the equations of motion.
Yeah.
You're getting the Killing spinor equations. What are you doing differently?
I'm calculating the renormalization not of my metric, yeah, of my B field, yeah, which would normally give you the equation of motion for the metric or the equation of motion for the B field, but I calculate the superfield equation of motion on the worldsheet for these functions that I have here.
Ah, okay.
And they kind of incorporate a lot of these information simultaneously. And that was what I also mentioned, that was also the observation by Hull, Lindstrom and company, where they also saw that this thing happens. So one other analogy where this thing is even more powerful, where you immediately of course can recognize the result, is if you do it for 2,2, so the standard embedding case. Then you just have a similar action within just the Kähler potential, and then you would just directly do the realization of the Kähler potential. You just get that it's renormalized with the log that of the metric. That's zero, that's the Clabeyao condition.
Okay. Well.
I just, could you try like beyond order alpha prime in the BPS equations?
We are currently working on that, so my student is halfway through, and then in the moment he just finished his master, so we have to see about when we continue that. But that's certainly what we plan for. So 2 loop we will certainly want to do, so that's the next order in alpha prime. And then depending on how complicated that computation was, you can even maybe wonder, can we maybe go 1 order further, which is really certainly out of reach with standard techniques.
Okay, so let's thank Stefan again.